record to this computer. Stop sharing. Cool. Thank you very much, Campbell.
Awesome. Thanks. Yeah, thanks so much for having me. Yes, I'll just get straight into it. Yeah, so today I'm going to talk about, yes, sort of new perspectives on quantum modularity that have sort of come up in the last couple of years, and then how this relates to three manifolds. So roughly, in a sense, I'll be talking about sort of this sort of new quantum modularity that I'll be talking about is something that's been observed for basically quite general classes of q-hypergeometric functions. And, all of this work is sort of been ongoing work of Don and Stavros from the last 15 years. So, most of the credit is definitely due to them. And some of the people I've been talking with about this recently is another PhD student of Don's, Matthias. But yeah. So the reason that this plays a role in three-manifold topology is that many of basic examples of quantum invariants that one can construct and calculate can be expressed as nice q-hypergeometric functions. So for nice classes of manifolds, you can write down formulae that are reasonably nice, and then you can actually do calculations and you can start testing these sort of things. And then this quantum modularity has consequences for the asymptotics of these functions, or these particular invariants in this case. And it relates the asymptotics of these invariants to the geometry of the underlying manifolds, which is quite nice. So I just want to sort of give a warning to start off with. This is really still sort of work in progress. And so a lot of it is, or some of it is still conjectural. And in terms of relating it to the manifolds, it's not clear to me, at least, how general a bunch of the properties will go. So for certain examples of manifolds where you can write down nice formulae, where their character varieties are, say, finite, there's a bunch of extra assumptions that maybe could be reasonable to, push the conjectures of this quantum modularity to there. But for sort of more general manifolds where you might have a connected component of the character variety or something like this, there might be some sort of different behavior. So this might only hold for certain types of manifolds, these conjectures in generality, but yeah, it's still interesting there's infinitely many manifolds that these things will hold for, and so it's still sort of giving us a bit of insight, I think. Okay, so the rough outline is I'll talk about a bunch of conjectures that people have on the asymptotics of quantum invariants of three manifolds. Then I'll describe briefly what q-hypergeometric functions are. And then I'll sort of talk about the original version of quantum modularity that Don proposed, I guess, about 10 years ago now. And then we'll see how that has been extended now and sort of actually creates a much nicer picture and is potentially slightly less vague than it was 10 years ago. Okay, so this first section, I'll just get straight into it. So there's a bunch of invariants. I was going to discuss them, but then when I timed myself, I didn't have enough time. So we're just going to assume that these things exist, and I'll sort of just describe them and give you some examples of them. So for a knot, we have the colored Jones polynomial, which is an invariant that is indexed by natural numbers. And for any natural number, it should spit out a Laurent polynomial, and this is an invariant of the knot. And so using this collection of invariants, we can define this so-called Kashayev invariant, which takes, roughly we're going to think of it as a function from roots of unity to C. And so it's going to take a root of unity, so Q, which is E of tau. So E of tau is going to be the exponential of 2 pi I times tau, for tau some rational number. And we define this Kashayev invariant to be the colored Jones polynomial colored by the denominator of tau evaluated at that root of unity. And so I'm just going to call this the zeroth color for fun. Okay, so this is how the Cache invariant is defined. And then we have this famous volume conjecture, which states that the asymptotics of this invariant relate back to the hyperbolic structure of the manifold. So if we have some hyperbolic knot, and then we evaluate this Cache invariant at E of 1 on n for some integers n tending to infinity, and multiply it by 2 pi divided by n, then this is equal to the complex volume of the knot, complexified volume, which you can think of as the Chern-Simons invariant of this knot, evaluated as the geometric connection, and plus I times the volume of the hyperbolic knot. Okay, so this has been around for quite a while now. I guess early 2000. And so then I want to talk about sort of the versions of this for closed manifolds. So this is quite well known. And then there's some other versions that talk about the quantum invariants of closed manifolds, which will be Witten-Reshetic and Shiraev invariants. I'll just call them WIT invariants. But before I do that, I want to briefly mention flat connections in case people are not so familiar with these geometric things. So here, if we have M, some connected 3 manifold, and we can talk about it with or without boundary, then we're interested in sort of these special connections, which are sort of flat connections. And so these are basically curvature 0 connections. And physically, if we were doing Chern-Simons theory, these would be like the classical states of the physical theory. So they're extremer of some, functional. And so, because you can describe these using differential geometry, but a nice way to think of them, and just an easy way to sort of start trying to write them down, is this algebraic description, which basically uses the holonomy of the connection to write them like this. But so I'll call the AM flat to be this set. So we take representations of the fundamental group of our manifold into SU2 or SL2C, and then we quotient by conjugation. And so this set we'll identify as a set of flat connections. So as I kind of mentioned at the start, so this is, you can think of as, or this is sort of also called the character variety of the manifold. And so this, the examples that I know of, this is always a discrete set. So for many 3 manifolds, this is discrete, often finite. And then in certain examples, you might have, say a curve or something like this. But for closed manifolds, at least, this is true. For manifolds with boundary, when you specify a boundary condition, often then you get a finite set, but if you let the boundary conditions vary, then you have a curve, which is the A polynomial, which you might have heard of. But so on this set of flat connections, we have a nice extension of the complexified volume. And so this is, giving us a map from these flat connections to C modulo 4 pi squared Z. And when we talk about SU2 connections, this lands always in R mod 4 pi squared Z. Okay, and so in this character variety for the complex character variety, so for SL2C connections, there is this unique, there's this natural point in this set that is induced by the hyperbolic structure of the underlying manifold. So each manifold has this unique hyperbolic structure, and this comes along with a flat connection. And so this is how it relates back to this volume conjecture, because here, we're seeing one particular, okay. But so then, so we've seen this Cache invariant has this asymptotic properties, and now we can, ask similar questions for this WIT invariant. And so this is maybe slightly older, this conjecture, but so originally, Witten sort of in this famous quantum field theory in the Colored-Jones polynomial paper, sort of argued that the Jones polynomial should be some quantum Chern-Simons theory for, maybe you could think of it as for manifolds with boundary. And you should be able to basically do surgery operations on knot and construct invariants for closed manifolds. And he said that this should somehow be thought of as an integral over all connections of the Chern-Simons invariant e to the n times the Chern-Simons invariant divided by 2 pi I. And this is for SU2 connections is just the complexified volume. Okay, so the right-hand side doesn't make any sense, but if it did, we should be able to study this integral asymptotically for large n by using a stationary phase approximation. So then we come up with this following conjecture. Also, yeah, so an important thing to note, which I have written but didn't say, is that here, because of the ambiguity in this Chern-Simons functional, n has to be an integer for Witten. So that's kind of an important point. But yeah, anyway, the way that we construct them in the end, we don't need this, but for Witten's interpretation, that's important. Yeah, so anyway, so if this thing existed and made sense, then we should be able to take a stationary phase approximation of it, is roughly the idea. And so then Witten's asymptotic expansion conjecture says that if we look at the WRT invariant evaluated at these roots of unity, E of 1 on n, then this should be asymptotic to a sum over the SU2 flat connections of e to the n times the Chern-Simons, evaluated that flat connection divided by 2 pi I. And then there's some polynomial growth out the front. Maybe there's a half integer power here, and then just some asymptotic series in 1 on n. And so mathematically, what this twiddle means is for any polynomial growth, you can take, so if I say I want this to decay like n to the minus 1 on 100 as n tends to infinity, then you can take enough terms in this series so that the difference of the left-hand side and the right-hand side decays polynomially in that way. So that's sort of mathematically what this statement means here. And so this has been proved for a bunch of examples, same with the volume conjecture. And then finally, sort of to tie between the closed manifold case and the this volume conjecture case is this sort of more recent conjecture of Chen and Yang, which I think is maybe like, I'm not sure if the archive paper was up in 2015 or that was the published version, but so around then, so sort of quite recent in comparison. So yeah, so they formulated this conjecture which said that if we sort of do the same thing we did for the Kashayev invariant, so we evaluate this WRT invariant at, now we take these roots of unity, so we take 1 on n plus a half, and so we just basically replace n by n plus a half from the volume conjecture. So if M is a hyperbolic manifold, then if we take this limit, this should give us the complexified volume of this closed hyperbolic 3 manifold. So this is kind of interesting because this behaves quite differently to the other to Witten's asymptotic expansion conjecture. So if we look back here, we can see that we have these exponential terms here, but because the Chern-Simons functional evaluated at SU2 connections is always a real number, this always lives on the unit circle. And so these are just oscillating terms. So this has polynomial growth at these roots of unity. But then we see as we go to this n plus a half, these roots of unity, we have this exponential growth, and it grows like this complexified volume, or the volume, and then there's this oscillating term, which is given by the Chern-Simons functional. Okay, so these are sort of different versions of sort of the same kind of thing. And so for the main sort of thing that I'll talk about today is basically unifying the Chen-Yang conjecture and this Witten asymptotic expansion conjecture. So the way that we can see that they're sort of part of the same structure is by basically this quantum modularity property. And so, yeah, I'm just giving lots of warnings, but so yeah, again, all of the sort of quantum modularity is always for these q-hypergeometric functions. And this basically, maybe one reason is because you can actually do really effective calculations for these things. And so, yeah, so now I'll talk about what these are and yeah, how some of their properties. Please interrupt if there are any questions. Okay, so yeah, so a q-hypergeometric function, so we can think of q here as maybe some sort of formal variable at the moment, or we could think of it as I mean, I'll talk about this in the next slide, but maybe you want to think of it as a point in the unit disk, or you want to think of it as a root of unity, but regardless, so Q is some variable. So f of Q is q-hypergeometric if it can be written as a sum over a lattice of some other function, f sub n of Q, and it satisfies some recursions between the different sum n's here as we change n. So here, if we shift the ith index of n by 1, and multiply it by some polynomial in Q and Q to the n sub I, then this is equal to some polynomial in Q and Q to the n sub I times the unshifted function here. So if this Ri is non-zero, what this means is that shifting this index is taking the previous function and then multiplying it by a rational function in Q and Q to the n when we can divide by this. Okay. So a little quick example is this function here. So just recall this nth q Pochhammer symbol here is a product of 1 minus q to the I from I equal 1 to n. So then this function here is one of the famous Rogers-Ramanujan functions, but that's besides the point. We can, this is an example of a q-hypergeometric function because if we look at this sum n, so g sub n is 0 for all negative n and is q to the n squared divided by the nth Pochhammer for n non-negative. And we can see that this sum n satisfies this relation here. So if I multiply by 1 minus q to the n plus 1 times the n plus 1th sum n, this is q to the 2n plus 1 times g of n q. And so here an important, what are the kind of things that we are allowed to have in this sum n? Basically, it's combinations of Pochhammer symbols, and this will give us terms like this in our polynomials. And we're allowed q to some quadratic form, because when we basically taking the ratio of q to the n squared and q to the n plus 1 squared gives you some linear thing here, which gives us a polynomial in these variables. So the fact this is quadratic is important, and the fact that we have these Pochhammers. So then one small remark about this definition that I've given is that, here I've I've been a little vague, but I haven't specified if this is for all n or if this is for some set of n. And basically we're allowed a little variation. So here generally we want it for most n for this equation to be satisfied. But for example, if we had a one-dimensional sum, we might allow this equation to break at 0 or something like this. So there's these conditions potentially, they don't have to hold globally. They can hold it on some large set of all n in the lattice, for example. Okay. So then as already mentioned, there's different ways that these q-hypergeometric functions can arise. So for different kinds of q. So the example we just saw, this Rogers-Ramanujan function, this is a q series that's convergent on the unit disk. But we can also take q to be a root of unity, and then these q-hypergeometric functions lie in this so-called Hypergenetic ring, which is defined as follows. So we take a directed limit over the integer polynomials in Q divided by the ideal generated by the nth Pochhammer symbol. And so then just from this definition, you can see every element in this Hypergenetic ring can be written as a sum of f of n q times the nth Pochhammer for some polynomial z of q, in z of q, sorry. So here you can see that evaluating at a root of unity will always give us a finite sum, because these Pochhammer symbols will eventually be 0 for infinitely many of them as soon as you get past the order of the root of unity. So we can evaluate at roots of unity, but sort of even better, we can actually substitute in, say, the root of unity times the e to the h, and then we get a formal expansion in h. each root of unity. So often people describe this as sort of analytic functions on roots of unity. So at each root of unity, we get a formal expansion in H, and this has this formal expansion is in the cyclotomic field, or has coefficients in the cyclotomic fields corresponding to that root of unity. And yeah, it will have zero radius of convergence, but we can still formally expand it and get out these series. So just to give an example, which we'll see again in 2 seconds, is this function j of q. So here, yeah, we can see basically we've got the pockhammers on top now, and then we can basically multiply it by whatever we want. As long as we have some pockhammer here floating around, we'll see that this is in the Hibero ring, and this is exactly the Kashayev invariant of the figure 8 knot. And so I'll go through some of the details of that in a second. But the last thing I wanted to mention for these q-hypergeometric functions is that they come with, they don't just come by themselves, they come with a whole set of functions. So here, a natural operation to do is basically take the summand, ignore this h, yeah, take the summand gn of q and multiply it by q to the bn. And so then we see that, so this function g sub b of q is given by this. And so this gives us a big set of functions. And then from looking at the relations that make this q hypergeometric, you can deduce a bunch of functional equations. So here, in this case, for this function g, it's actually written in terms of like all of these, like potentially we think we get infinitely many functions, but really we get Laurent polynomials times a basis of 2 functions here. And so this big set of functions, which actually has a sort of nice basis in general, this will be important for the modularity that we'll see a bit later in constructing sort of the certain aspects of the the sort of potentially you could think of as new invariants from these, but potentially not. Okay, so now I want to talk about what was quantum modularity 10 years ago for those of us who don't know. Okay, so there's sort of, so Don originally, when he originally introduced it, he sort of didn't give a very sort of rigorous definition or a strict definition because it wanted to capture this idea that came up in different areas. And, you know, it was more of the way he describes it is always, a group can be potentially vague, like there are quantum groups, which are obviously very different to groups, and, they still have a similar sort of flavor potentially. But so the way that I'll describe it here is that a function from Q to C is a quantum modular form of weight K if and only if for any gamma in SL2Z, sorry, so these are integers, if we take the difference of f of gamma of tau minus this automorphy factor c tau plus d to the k times the unacted on function. So if this is more analytic than f, then we say that f is a quantum modular form. So one thing to note, because we're looking at functions on Q, I mean, if we had some sort of stricter sense of modularity, this would be trivial because Q just has one orbit. So this at least gives us some room to play around. We'll see that there's better versions of this definition later, but this is sort of originally how it was described. And so then I'm just going to jump straight into the interesting examples from geometry and topology. So this was the first big interesting example there, which is, of course, you do the simplest hyperbolic knot. So the figure 8. So this is its Kashayev invariant. It has this nice formula. And yeah, as we saw, this is something that lives in the Hibero ring. So the original observation that Don had, which is this is now a theorem, is that yeah, so if we take the Lexified volume, it's given by this number, which you can, all of these volumes you can evaluate using triangulations and then dilogarithms. So this can be given as an exact number. So yeah, so if we take tau and we send it to infinity and we bound the denominator of tau basically so that we have some sort of uniformity, then if we take the difference of log of the Kashaev invariant evaluated at -1 on tau and just log of the Kashaev invariant evaluated at tau, then asymptotically this looks like v times tau divided by 2 pi. So here we see exactly what we expect from the volume conjecture. And then we have a full asymptotic series. So here we have this log term, and then we get a nice asymptotic series in 1 on tau. Okay. So yeah, this right-hand side at the moment, or the way I've written it is just as an asymptotic series. So it's not so analytic because this is divergent. So you can think of this difference as maybe like a limit of piecewise analytic functions or something like this by taking optimal truncation. But so just to give you a feel for how this fits into this quantum modularity framework, how this is more analytic, I've taken these pictures from Don's original article. So if you plot this logarithm of the Kashaev invariant, it looks something like this. So it's a bit of a mess. I mean, there are some patterns that you can kind of see with your eye a little bit, but you know, it's quite chaotic. But then if we take this difference, then we see that now it's behaving sort of in a much nicer fashion. So here it's jumping at every rational. So it's not so analytic, but it's definitely got more structure than this function here. So yeah, so this sort of isn't as nice as we'd want. It'd be nice if we could say get out sort of a smooth function in the end, but here, yeah, this is as good as it gets. And so before I go on to this sort of, you know, the new versions of this, or how we can basically, in the end, after we take the proper sort of version of the quantum modularity, we'll end up getting smooth functions out at the end. But so before I do that, I just want to mention how these things are proved for, yeah, at least these Carl-Jones polynomials where you have a nice q-hypergeometric expression. And so it effectively relies on a modularity property of the Pochhammer symbol. So it's sort of summed up in this expression here. So if we take the Pochhammer at the kth Pochhammer evaluated at gamma of x, then this is the Pochhammer evaluated at x, where now we have to take this new index here where we take k and we divide by x. We might have to take the absolute value and then take the floor. So there's sort of some jumping that's happening at certain points. And so then we have this function here multiplied by some nice analytic function with this periodicity property here. And so this is sort of the main fact that you need to prove the yeah, these kind of statements. Okay, so the proof of this is basically just some third-year complex analysis. You want to write out this sum here. So you take the logarithm of the left-hand side. You want to write out this sum as an integral by doing some contour integration. And so this is effectively just a variation on the Abel-Planar summation formula. And so then what leads to this Pochhammer symbol here appearing is basically the branch cuts of this function here. So when you do this contour integration, you have to go around these branch cuts, and that's why there's this floor function appearing, because at certain points you get another branch cut and you jump up by one of these values here. That just gives you a flavor for how the proofs go. And just for the asymptotically minded people, this is sort of roughly the expression, or this is the first order expression for this f of gamma function here. So you can see that it's always a function everywhere that k appears, it's always a periodic function on k divided by x. And here, of course, we see this dilogarithm appearing, which is why for the manifold cases, it relates back to the volumes of the manifolds. So this dilogarithm is important for that. Okay, so yeah, so now I'm going to go on to this newer part. And so this is sort of, I guess, where there's still a lot of proofs that need to be done, but this is maybe you can just get an insight into the experimental observations that we've had, and Don and Stavros, I think, have some proofs in some examples. But yeah, for the examples that I've looked at for the WRT invariants, this is still conjectural. So yeah. Yes, okay, so let's sort of have a closer look at this asymptotic statement. So if instead of taking the logarithm, we just look at the function j, then asymptotically, it behaves like this. So we have some exponential term that's growing. So this was that linear term at the start. And then we have some function here which had a asymptotic series in, tau to the half, basically. So it had some nice asymptotic series, but it didn't converge. So it would be nice if we could turn this into a function. So the way that we do this is either via some optimal truncation. So here you basically just sum up a finite number of terms in your series, and you choose the point that you stop summing up depending on how large tau is. And so Don and Stavros have come up with some new numerical methods that they call smooth optimal truncation, which sort of should lessen, basically, because I mean, this is going to jump at certain points as we go from where we've summed up this many terms, and then we start summing up the next term, which depends on tau. And so that's going to create a jump at some point. And so then there's going to be some bound on the error of this function. Like there's no, it's definitely not approximating an analytic function very well at those points. But there's something you can do which sort of smooths out those jumps. So that's one way that Don and Stavros have been doing, or been turning this thing into a function. Another sort of way that just seems to work quite well is this Borel resummation. So this is related to basically resurgence of this asymptotic series. And you can do this numerically and construct some analytic function here that has the asymptotic properties you want as tau tends to infinity. But so when you do that, so you have to do something here. That's sort of the tricky point. You turn this from an asymptotic series into some function. But then when you do that, we want to subtract the right-hand side from the left-hand side and see what you get. Is that all? Is this like how well does this, when we've turned this into a function, is it giving us this full function here? And in fact, no. So if we take the difference and then we look at the asymptotics again, we actually see another power series or another asymptotic series popping up that hides underneath the exponential growth of this function. And in fact, this series is just the series we get from the fact that this J function is an element of the Hibiro ring. So if you recall, I said elements of the Hibiro ring have formal expansions around each root of unity. And this power series that we see here is just the power series that comes from the formal expansion of J around 1. So we see this pop up and we know what it is. And so that's kind of cute. And so then we want to do exactly the same thing we did up here. This is an asymptotic series only, or a formal series only. And so we want to turn it into an analytic function. So we do that by some resummation or something. And then we do the same thing. We take the difference and then we look at what we get. Is that everything up to the level of accuracy we can do? And the answer is no again. And so here now we see an exponentially decaying term that appears. So here we have this exponential growth. Here we just have this polynomial growth. And then here we have an exponentially decaying term that you can see numerically. And then here we get another asymptotic series, which is just because we're dealing with the figure 8 knot, and it's got this nice, it has some nice symmetries. This is just the same series as this one with a minus sign. But then out the front of this function, we get some u function q of tau, which depends on tau in the rationals mod c. So here, this is just some new function, and we can basically calculate it numerically and start playing with it. And so a bunch of the properties that it has is that, so for one, it lives in the cyclotomic integers generated by the root of unity corresponding to tau. So you can evaluate, you can recognize this as an exact number. It has a nice Galois invariance property. So as we change this root of unity, we can change it before or after we evaluate the function, and that gives us exactly the same answer. And so these are sort of very basic things that you need for this Q to be an element of the Hypergenetic ring. But there's a bunch of more complicated congruences that you can also check in this case, and they satisfy it. So it looks like we have an element of the Hypergenetic ring. So then it would be nice if we could get a formula for it. And because J was q-hypergeometric, I've already mentioned that we have these nice q-holonomic modules, which gives us a set of functions. And so it's sort of natural to guess that this function could live inside that q-holonomic module. And in fact, if you do a search through that module, then you find that, say, up to tau with denominators 200, you could probably do it up to denominators with 1,000 or something. You see that this q of tau is given exactly by this expression here. So we see the same sum and then we multiply by -1 minus q to the n here. Okay. So then putting that all together, if we just rewrite our functions in this way, so we just call 1 j0, j1 j, j2 q, then we have an expression of this form. So we have these phi hats have these exponential terms. So here there was these exponential, this was polynomial. This had exponential growth and this had exponential decay. And then we just have an asymptotic series in tau. So yeah, here they are. So here, if we do resummation to all of these asymptotic series, then this actually becomes an equality, which is quite nice. And so here, now this also looks sort of quite close to Witten's asymptotic expansion conjecture, because here we're summing over, for the figure 8 knot, we have the geometric connection, we have its complex conjugate, and then we have the trivial connection. And so all of these terms correspond to one of those flat connections. So here we have the asymptotics of this quantum invariant look like a sum over all of the flat connections, not just the geometric. It just happens that the geometric is the largest contribution, or has the exponential growth. Okay. Yeah, so anyway, so that's just for this J1. And so a natural thing to try and understand is for this new function that's constructed, J2, what are the asymptotics there? And yeah, in that case, we can find another set of functions, phi hat. So they're going to be of the same form. They're going to have these exponential terms out the front, and then multiplied by some formal power series. And when we do that, we can write out the full modular transformation in this form. So if we take this vector of J0, J1, J2, then this is equal to, the vector just evaluated at tau multiplied on the right by this function with these, now we want to think of them as analytic functions at most points, or at all but finitely many points. But yeah, originally we sort of came to them as asymptotic series that we've turned into analytic functions. Yeah, so this is kind of a pretty nice property. And so in fact, I definitely don't have time to talk about it today, so I won't, but you can extend this vector to a matrix in some other complicated way. But what's nice about doing that is that you can invert that matrix and get a formula for this matrix here. And so then we can just look at this matrix as, this matrix now we have these sort of interesting analytic functions with interesting asymptotic properties. And then, so we can actually understand that matrix for all gamma as giving us a cocycle in some sort of group cohomology. So here, it actually gives us an element in the first cohomology of SL2Z valued in, this should be 3 by 3, I guess. Yeah, it should be a 3 by 3. Matrices with coefficients, analytic functions at all but finitely many points in R. So it's a bit of a mouthful. And so here, the way that this group cohomology is defined is there's some twist because it acts on the arguments of these functions. But yeah, this is nice because we're actually sort of understanding how this modularity property should be given in some way. And so here, I've plotted at all of the hundredths tau with denominator 100, what this function looks like when we've normalized. And you can see, besides the little flaws, because I've only done it at 100 points, you can see this is looking much smoother than the original difference we gave for J. So this is sort of a much nicer realization of the quantum modularity than we had originally. Okay. So anyway, so that's sort of Don and Stavros's story for the figure 8 knot, and I've contributed a little bit to sort of recently, but so now I want to talk about the closed manifold case, because I want to get to this, how this Chen-Yang conjecture and the Witten asymptotic expansion conjecture fall under the same thing. So back, I think, late 90s, maybe early 2000s, Lawrence and Zagier looked at the WIT invariant for the Poincare homology sphere, this sigma 235. And so there on this manifold, we have two SU2 connections and a trivial connection. And one can do a bit of work and find that the WIT invariant is given by this nice q-hypergeometric sum here. And so defining W1 to be this invariant and W2 to be this similar thing, again in the Q holonomic module that corresponds to this q-hypergeometric sum. We find exactly the same kind of equation where now we take this phi hat to be given by this form. So here, it's because it's non-hyperbolic, it has particularly nice properties. And so here we can actually write down what these analytic functions are exactly in this bottom square matrix. And then up in this top part, we have these formal expansions again, but some analytic version of these, maybe the Borel resum of these. And so we see that, when we add in this extra function, that we get this vector, where if we take one on the vector evaluated at -1 on tau, this is the vector evaluated at tau, multiplied on the right by this cocycle, SL2Z cocycle. So that's kind of nice. And so how this is completely, this is all proven in this case because it's particularly modular here. But so then how this relates back to the Witten asymptotic expansion conjecture is, so if we look in here, we see that there's exponential growth as tau goes to infinity, there's oscillation as tau goes to infinity, given by this E of tau divided by 120, and here it's 49 tau divided by 120. And so to relate this back to Witten's asymptotic expansion conjecture, we see exactly that the complexified volumes, or the Chern-Simons invariant for the two flat connections we have, are given exactly by 1 on 120 times 2 pi I squared, and 49 on 120 times 2 pi I all squared. So that's nice. And so, yeah, so here I kind of said that it's particularly modular in this example, and that's because you can actually write out the invariant as a Eichler integral of an actual vector valued modular form. But so this is sort of all known. Maybe it wasn't packaged in this nice equation here that we have now. But yeah, this was kind of all known. But so then sort of how does this relate to a hyperbolic example? So I'll try and wrap this up quick now. So
about 10 minutes.
Okay, great. Cool. Yeah, okay, so then Okay, so if we take this function here, it's a little bit of a mouthful. I'm sorry, but that's just the way it works, unfortunately. But so here we have some function in Q, and we have basically the beta and the gamma are determining or sort of giving us this Q, they're kind of like the B that we saw for the Q holonomic module before. We're just multiplying the original sum n by Q to the beta of M and Q to the gamma of L. And then we have this little delta here as well, which comes from the fact that this POC has the two variables we're summing over in the bottom. But regardless, this is some set of functions that lives in a nice sort of rank 8 Q holonomic module. And yeah, so then one can show, I mean, this is where it came from originally, that the WRT invariant for half surgery on the figure 8 knot is given by a particular specialization of this function. So yeah, so this is an integer homology sphere. It's hyperbolic. Yeah, and it's closed. Okay, so then, yeah, so then we have this WRT invariant, and then you can sort of go do a similar story here. It's rank 8, so we have to find 8 of these functions. So numerically, this is a lot of work, but you can do it. So just certain combinations of these functions for particular beta, gamma, and delta. You can write out all of these things, make it into a big vector. The 6th is going to be our WRT invariant. And then we find exactly the same thing, of course. Where here, the exponential, we have, these phi hat terms in this matrix are given by, again, they have this sort of exponential term, which is dictated by the complexified volume of the connection we're evaluating at. And then we have some analytic function, which has an asymptotic series in tau to the half, effectively. And this little asymptotic series here actually has particularly nice arithmetic properties. And so it lives in, the coefficients live in some field, which is associated to the manifold, the trace field of the manifold in particular. But yeah, so yeah, we see exactly the same thing. And so for the WRT invariant in particular, we see we have a sum over the flat connections, the SL2C flat connections, multiplied by each of these functions at tau. And we have this exponential term, blah, blah, blah. So this looks like Witten's asymptotic expansion conjecture. However, there's this function here that wasn't there. And we're also summing over the complex connections, the SL2C connections instead of the SU2 connections. So how does this relate? So let's just look at this function evaluated at the first few rationals. So here, yeah, if we evaluate it at 0, so this is the function evaluated at any integer. We have this vector here. And then, okay, we have them evaluated the first few others. There's just a bunch of terms, whatever. The important one is this, because if we see here, for Witten's asymptotic expansion conjecture, tau was always an integer. So here, this is always evaluated at an integer, which is just the same as the evaluation at 0 because it's periodic in Z. Okay, so then here, if we look, we see that 2 of the terms don't contribute here. And so if you look at this manifold, the indexing I've done is just because that's what Parry spits out when you do it. But yeah, so 0 is the trivial connection. 1, 2, 4, and 5 are SU2 connections. So here we see the SU2 connections are all contributing for the Witten asymptotic expansion conjecture. 3 is an SL2R connection. And so we see that that doesn't contribute because, because here that will vanish. So we don't see the SL2R connection. 6 is a geometric, as we already mentioned. So here again, we don't see that either. So we're just seeing these SU2 connections and the trivial, which is also SU2. Then we do see this term here, but this happens to be, this is the complex conjugate of the geometric. And this has exponential decay. So in terms of Witten's asymptotic expansion conjecture, it doesn't matter if we don't see this because of the way that I described that twiddle in that particular conjecture. So then we see that this conjecture, this modularity here, returns back Witten's asymptotic expansion conjecture as a special case, and in a lot more detail in regards to these functions. But so then, to get the Chen-Yang volume conjecture, we just have to note that looking at the geometric term, which is the WRT invariant term, so evaluated at an integer plus a half, we have this equaling 2. And so then if we go to this asymptotic statement, this asymptotic expression, or this exact expression when we've turned this into a function, as tau is going to infinity, there's the geometric term will have exponentially increasing asymptotics. And this is going to then dominate every other thing. So that's all we're going to see. And so the fact that now this is non-zero for this half integer means that we get exactly back this Chen-Yang volume conjecture, because we're looking at the largest exponential growth that we see, and that's going to be the complexified volume. Okay. So maybe sort of to try and package it up optimistically. So as I mentioned, there's so many provisos, but optimistically, you could potentially come to the conclusion of this, optimistic conjecture that, so for say M closed hyperbolic 3 manifold, say maybe the flat connections need to be a finite set, then you could hope that there exists some vector W row indexed by the flat connections and some matrix phi of rho and rho dash, such that the geometric can, the vector evaluated at the geometric connection gives you back the WRT invariant, and it satisfies this modularity transformation here, where this has nice, asymptotic properties. So potentially, underlying this a little bit is basically, trying to understand the resurgence of these asymptotic series here in some way. But so anyway, this is potentially a version of a conjecture, if we're optimistic. So that sort of puts them under the same label. Okay, so then to finish up, I just wanted to mention that you can do similar things with Q series. So here we're talking about WRT invariants and Kashayev invariants, and these are all evaluating at roots of unity, but there are sort of Q series invariants of knots and 3 manifolds that have been constructed recently. And there you can do a similar thing. You'll see exactly the same kind of expressions. You'll see exactly the same kind of expressions here, where now here it won't just be evaluated at a root of unity. It will be, so here it will be a Q series, and here it will be like a Q tilde series or something. So these will have exponentially small terms. But so you can do the same thing there, and then you can use that to understand this matrix, this phi hat matrix, not just for real numbers, but for for numbers, say, in the upper half plane or the lower half plane as well. But here's something, there are some interesting things that happen when you deal with the Q series, which is that sort of in different regions, in different regions, there's certain jumping that happens, which is related to the fact that we've tried to take or maybe if you're in from a resurgence point of view, you've tried to take this asymptotic series, turn it into an analytic function, but the asymptotic series had, I mean, it had sort of some, basically when you do the Borel transformation, it has some branching that's appearing. So there's sort of some jumping that happens, and this is called Stokes phenomenon. And so then you can see that in the Q series setup. But there are some conjectures relating how, like understanding that Stokes phenomenon and relating it to Q series invariants of knots, which is this 3D index. And so that should be related to somehow BPS counting or something. But so this is sort of another direction. And so what I'm currently working on is sort of, understanding sort of, finishing off this 4-1 story in the Q series setup, which is interesting because it's introduced some sort of new functions, which are these quantum Jacobi forms. And so they're sort of the quantum version of what a Jacobi form is to a modular form. And so then what's nice about this Q series setup as well is it sort of, because there are descriptions of these Q series via state integrals, you can actually get to a bunch of proofs of a bunch of the modularity statements you want. And so this is sort of some of the stuff that I've been thinking about more recently. And so I think a really interesting outcome is that you can understand resurgence of these asymptotic series coming from physics via these modularity properties, and sort of I think it should be a good playground for people to study resurgence. And then some little quick questions, which and then I've got my references. So some questions that I'm interested in that are sort of a more geometric flavor are, so from the WIT invariant, we construct a vector of WIT-like invariants. And what are the other components of this vector is not clear to me geometrically. They come from this modularity, but what do they mean geometrically? Are they related to, so you can think of these q-holonomic modules as like a quantization of the character variety, and you can think of the so-called skein module of a 3-manifold as sort of a quantization of the character variety. And so, it would be interesting if these were somehow related to the skein module in some way. But I don't know so much about that. Another interesting question, which, so people are often interested in these hyperbolic examples because they're sort of the harder ones, but a question that sort of is of interest to me is what connection gives back the WIT invariant. So for the hyperbolic things, we always have the geometric connection corresponding to the WIT invariant. But for non-hyperbolic manifolds, we have to choose some connection that should correspond to the WIT invariant in this vector. And for me, it's not clear what that should be in general, because that's that would be it would be an interesting that would be an interesting problem, basically, from there's certain questions relating to like the block group and K-theory, where you sort of would like to have a canonical representative of a certain solution to some equations, and it's not clear how to do that in general, but here it seems like the WIT invariant picks out some sort of connection or solution to some equations in a nice way. So that's kind of a potentially interesting question. And then, of course, for more interesting 3-manifolds, what happens? Do we still see the same kind of modularity properties? Do we get now a function on the space of flat connections, and then the right-hand side where we had a sum over flat connections, does that get replaced by an integral over the space of flat connections? They're sort of interesting things. And here are all the references. Thanks so much for listening and having me. I hope it was helpful. Sorry there weren't so many pictures.
That's all right. Thank you so much, Campbell. Does anyone have any questions? Feel free to unmute and ask away. All right. I have one question, which is.
Hi, Ellie. It's James here from.
Oh, sorry. Yep, go for it.
Yeah, I wasn't going to ask a question. You go.
Well, all right. I thought I heard someone. Can you kind of give an intuition as to what like more analytic means, or like, this is somehow a very vague thing where you can define more in various ways.
Yes. Yeah, so I guess the takeaway of sort of this sort of newer perspective is that it's really analytic everywhere except for particular points that you know. So it's analytic. So for example, for the S matrix, so in this setup, so the difference originally for the quantum modularity was giving us sort of the logarithm of one of these phi's roughly. And yeah, so basically we're sort of talking about the analytic properties of these phi's. So, but with this whole vector valued and this matrix of phi's set up, here more analytic means very much analytic everywhere except, so for the S matrix, it would be at 0, for example. So it's analytic in the positive reals and the negative reals, but there's some discontinuity at 0. So that's one. So that's a nice outcome of this, where we can say sort of more analytic. We actually want, so let me go back. We really want something of this form where, yeah, this is a cocycle that lives in that group cohomology. And that had, yeah, these actually analytic things, not sort of germs of analytic things at each point. So yeah, so I think that's the answer that I'd like to give.
Cool, that helps. Any other questions?
Yeah, I wanted to ask a question. Sorry about background sound, but
That's right.
so I just wanted to ask about your conjecture. I guess my question is, you've done this for some examples, and I was wondering whether like the calculations you've done in those examples will give you an idea about how to prove this, or whether the proof will go a completely different way. Can you give us a quick version?
Yes. Yeah, so I mean here, so yeah, so a proof is gonna, so it's gonna be roughly similar to the proof that I just, or the idea of the key fact for the proof of the old version of the quantum modularity. So it's really, you really need to use the modularity of these Pochhammer symbols here. And then the fact, so it's always going to be these Pochhammers, and then you have some quadratic form here. And then you have some linear term, which is sort of giving the q-holonomic module. But so the reason that these, so yeah, the proof looking at a formula like this is kind of potentially, with a very careful analysis, you could potentially do something, because these functions, you can almost guess them by looking at the form of this expression. When you do the asymptotics, or you do the sort of modularity, write it down explicitly for these sum ends and how it goes, all of these different functions appear basically because there's branching of the dilogarithm. And so when you sort of look at the critical points in this sum, for the sort of the leading asymptotic term, you have to correct them by the sort of different branching that's going on. And that correction is exactly what leads to these linear terms appearing here. So yeah, potentially there would be some hope to get proofs by doing a very careful analysis of that. So the tricky thing here is that, yeah, the really tricky thing is that you're taking these asymptotic series and you want to make them into analytic functions, which is important because you can't sort of, yeah, you can't, if we just have an asymptotic statement, so if I just had this as an asymptotic statement where these are asymptotic series, it doesn't make sense. Like, in what sense do I mean it? Because there's this exponential term here, and so therefore the term with the largest exponential growth, you can't see, you shouldn't be able to see the other terms with a little twiddle, for example. And so that makes the analysis quite hard to be very precise in that sense. But there is some sort of, yeah, so you can guess these from this formula, so that sort of indicates that there should be maybe some, if you're smart enough about it, you could potentially prove it in examples like this. And if you can do it in one of these q-hypergeometric examples, then you effectively should be able to do it in all of them, I guess.
Cool. Thanks so much. I'm going to stop the recording now and create probably 3 breakout rooms for all that want to stick around. But if we could once again thank Campbell for his wonderful talk,
Thanks.
that would be great. So thank you very much.